Okay, so finally in this lecture we're going to prove that our rings of integers are finitely generated. Z-modules, that is. Finitely generated. Okay, so the overview for this lecture is fairly simple. We're really just going to prove this one fact using our previous tools that we've developed over the course of several lectures. So, goal, we're going to prove rings of integers are number fields are finitely generated Z-modules. I guess we're going to prove something slightly stronger where if the field has degree m over q, then that will be the oh, sorry, yeah, I guess we're going to prove something even stronger, which is that not only are they finitely generated, they're actually free Z-modules. I guess maybe this is kind of obvious. There are no a finitely generated Z-module is free if and only if it has no torsion, and I guess maybe like if we know they're finitely generated, then the fact that they have no torsion is fairly clear, because the integers, there are no zero divisors basically. Okay, so what's the idea for this proof? So the idea okay, so we're going to use our non-degenerate trace form to find modules, find Z modules. These are going to be free Z modules. I should say free Z modules of rank M. Let's say, and this is, you should be thinking of M as being the degree of the extension over Q, our number field. Which basically sandwich our ring of integers. So our ring of integers is going to fit between these two free Z modules. And then from here, the result will follow basically from general facts about finitely generated modules over a principal ideal domain. Then the result will follow from the theory of finitely generated modules over a PID. Okay. So our main result is the following proposition. So this is going to be 22.1 proposition. So we're going to let A be an integrally closed domain. Integrally closed integral domain with field of fractions K. And okay, so we're going to let B be the integral closure in some field extension. Integral closure of A inside L, a separable extension of degree M. Okay. And then the result is then there exists A submodules let's say M and M prime contained in L, each free of rank M, such that the sandwich B M is contained in B is contained in M prime. Okay, so we're going to construct these two submodules M and M prime. One will be easy, and then the other is going to basically we're going to construct a basis, an integral basis for L, so a basis of L that lies in B by clearing denominators, and then we're going to take the dual basis and take the A module that generates, and then those will give rise to these two. So let's go ahead and see this in action. So I'm going to let beta 1 through beta M be a basis for L over K. Okay, so we know from our lectures on the basics of rings of integers, since we know that L is the fraction field of B, we can find a common denominator. Common denominator D. We could really choose this in A, but it doesn't matter. It suffices to choose it in B, such that D times beta I is in B for all I between 1 and M. Okay. Note that basically this collection of D beta sub I, this is still going to be a K basis for L. This is what's called an integral basis for L. A K basis for L, and we're going to let M basically be the submodule generated by these. Basically, without loss of generality, we could assume that our beta sub I started in B to begin with. So without loss of generality, let's just assume that beta sub I was in B. And we're going to let M, this is our first guy, this is the A span of the beta sub i's. Okay. So a small note, since these things are linearly independent over k, they're certainly linearly independent over a. So note beta sub I, the collection I equals 1 to m, form a basis for m as an A module, and hence m is free of rank m. Oh, 2m's floating around here. Should be a little okay. So we've already got our one candidate in our lecture. So in our previous lecture, lecture 21. So in our lecture on discriminant in number fields, discriminant in number fields. So this is lecture 21. We saw that the trace by linear pairing, the trace form, was non-degenerate. Okay, remember this amounted to basically using some Galois theory to reformulate the formula of the discriminant in terms of so basically we use our formula for the trace that involved Galois conjugates. Then we use this to rewrite our discriminant formula, and then we use like linear independence of characters basically to say that the discriminant of the trace form was non-zero in the case that L is separable, a finite separable extension of K. Okay, so now if you remember from our lectures on bilinear forms, this means we can form the dual basis. So we're gonna let let me see what exactly I called them. Okay, so we're gonna let gamma sub I equals 1 to m. We're gonna call this the dual basis. The dual basis. So remember what this means. To the beta sub I. Remember what this means. The dual basis. So that the defining property of the dual basis is that the trace from L over K of beta sub I gamma sub j is 1 if I equals j and 0 else. Okay. Remember this, to construct a dual basis, you basically use the bilinear pairing to give you an isomorphism between L and the linear dual, and these gamma sub j's are the elements which map to the dual basis of the linear dual to L. Okay. And if this is confusing or you're not understanding what I'm saying, I would go back and look at the lecture on bilinear forms. Okay, so see lecture on bilinear forms. Okay, so we've got our next candidate, so we're going to let m prime, this is going to be the A span of the gammas. Okay, and again, this is a free a free A module of rank M, it remains to show that B is contained. That B is contained in M prime. Clearly, M is contained in B since each beta sub I is contained in B, and B is an A module. Okay. Okay, so this is kind of I guess this is kind of the clever part. So we're gonna let B and B, and since the gamma sub i's form a K basis, we can write B is the sum C sub I gamma I, where a priori we only know that these C sub i's are in K. So the next question is, how do we, so I claim each C sub I claim each C sub I is an A. Okay. So note, basically, the idea is to use the trace form to kind of pick off these C sub i's. Note that the trace from L over K of B times beta sub J, well, the trace is K linear, so this is the sum from over Ci, the trace from L over K of gamma sub I beta sub J, and the only term we're going to pick up is, so this is going to be 0 when I is different from J, and it's going to be 1 when I equals J, so we're just going to get C sub J. Okay. Since B times beta J, right, this is certainly in B, and hence is integral over A. Thus, the trace is integral over A as well. I think if you review our lectures on norm and trace, maybe norm and trace and like Galois theory or something like that, you'll find this proposition that tells us that since this is integral over A, the trace is also integral over A. It's basically the sum of some Galois conjugates, each of which is integral over A. Is integral over A. Since A is integrally closed by assumption, integrally closed, C sub J, which is the trace L over K of B times beta sub J, lies in A. Okay, so this finishes the proof. Since we can choose these C sub i's to be in A, every little b in big B is in the A span of these guys, and hence B is contained in M prime. This proves that we can necessarily sandwich B between two free A modules of the same rank. Okay, so how does this lead to the proof? So this is 22.2 corollary. We're going to let L be a finite extension of Q. L will be a finite extension of Q. This is automatically separable because we're in characteristic 0. Let's say of degree M. Then O sub L is a free Z module of the same rank. of rank m. Okay, and how do we prove it? Well, we just saw that O sub L, so by the previous result, there exists M and M prime Z submodules of L free of rank M. I always do that. Should be little m, such that with, they have to sandwich O sub L. And then you just use the fact about then the result follows from the following. Okay, so you need the following fact from algebra. If R, I guess maybe I'll state it like this. If, let's say, N is a free module of finite rank, N is a free module of finite rank over a printable ideal domain. So over a PID. And let's say M subset of N is a submodule. Then basically M is free of rank. Free of rank at most that of M. N. Free of rank less than or equal to the rank of N. Okay, so this fact, I'm not going to prove this fact. It basically follows from the existence of Smith normal form matrices. So this hopefully is review. If not, you can find this in something like Dummett and Foote. Okay, and maybe at some point I'll do a whole lecture series on just general algebra, but yeah, so that pretty much finishes the proof that rings of integers are finitely generated Z modules. So in the subsequent lectures, we'll hopefully do some examples of finding rings of integers, and we'll talk about some of the techniques you can use to compute the discriminant and how you can use the discriminant to actually tell if you have a basis or not. Okay. You can see in this lecture we used a lot of the previous machinery. So at least if you want to do this proof, a lot of this machinery actually really was necessary to build up in order to prove this result. Okay.